In this video, let's have a proving exercise about the mean. So prove or disprove that at least one of the elements in a finite set composed of integers, example x sub 1, x sub 2 until x sub n, is greater than or equal to the mean of all elements in the set. So there are plenty of ways to get around this problem, but let's try direct proof, and later on let's try contradiction as well. So by direct proof, we could say let one element, say x sub k, will be the largest element in the set. And that's largest element x sub k will be, so if this is set as an element of your set S, and basically we're going to prove that your x sub k, the largest element, will be greater than or equal to your mean. So for example, this is the mean. So by assuming that x sub k is the largest, we have an idea that x sub k will be larger than your first element, say x sub 1. So it is also larger than your x sub 2, or larger or equal to, because all elements could be equal, and so on until the last element, say x sub n, when there are n elements. So again, this is part of the assumption that xk is the largest, and then you have to prove this one. So you're going to prove that x sub k will be greater than or equals to your mean. And the way we go around with that is by simply adding the elements in the assumption. Say if we're going to add x sub k greater or equals to your first element plus the second equation, x sub k greater or equals to your x sub 1 plus x sub k greater or equals to the last element. So how many x sub k's are there? There will be n in terms of the number of elements. So it will become n elements by x sub k, and that will be greater or equal to, so x sub 1 plus x sub 2 until x sub n. That will be the summation of x sub I, where the index will be from 1 up to n. And by simply dividing or multiplying them with 1 over n, so we will get the mean here, and this will be x sub k is greater than or equals to, basically this 1n times the summation, and that is basically equals to your mean. So therefore x sub k is greater than or equals to our mean. Hence, we have proven this one. So this is by direct proof. Another way of going around this problem is by contradiction. So if we're going to come up with a contradiction, we must assume the negation of the statement. So that means for all elements of x, say for all x element of, say, set S, you have the property x is less than the mean, for example. So given this idea, we have the assumption will be, so x sub 1, for example, will be less than your mean, and you have x sub 2 will be less than your mean, and so on until the last element. So x sub n will be less than your mean. And again, similar to the one that we did, or the technique that we did with direct proof, we're going to add these assumptions. So when we are going to add them, so we'll get a total with which will be the summation of x sub I from I equals 1 up to n, and this will be equals, or this will be less than your n times the mean x bar. So if you are going to multiply this with 1 over n, so 1 over n, so this will cancel this, and we will get the mean will be greater than the mean. So this is now a contradiction. When you have the mean as being less than itself, so plainly a contradiction, because this is the definition of a mean. So with this contradiction, the original statement is true, that at least one of the elements of a finite set is greater than or equal to the mean of all the elements in the set. That's it.